Hello everybody. In this video we will discuss acid catalyzed hydrolysis reaction of esters. So what are esters? So esters are a functional group when you have this particular group CO and O. Okay, so that's our esters. So how do we do these reactions? Finding the product in these type of reaction is extremely easy. So we can find the product since this is a hydrolysis reaction. So it's lysis. That means it's breaking into two parts, and you're breaking into two parts by hydro, which means water. So you are breaking the bond here. So I will teach you the shortcuts first, and then we'll go over the mechanisms. So you're basically adding water across the CO bond right here. Okay, so that's how you hydrolyze an esters. So the product would be, I will keep it as it is, how we draw it here. So that's, we separated this half and this half. Okay, so we will get our CH3O and H. So you can see the water get attached across the ester functional group, so it break them apart. So let's look at the mechanism, how the ester hydrolysis reaction happens in acid catalyzed reactions. So mechanism, so let's begin here. So we have our CH3CO OCH3, and then we have acid catalyzed water. So here so when you have acid in water, the acid is gonna stay as it is as H3O plus molecules, right? H3O plus molecule. So instead of writing H3O plus, let's just write HB plus. So B stands for anything that has a proton, right? So in this case, water. So what would happen is, we know that the oxygen has lone pair. Okay, so the oxygen has lone pair, and this lone pair will immediately abstract the proton. So we will immediately abstract the proton right here. So some people might ask, why not this oxygen? Why this oxygen didn't abstract the proton to begin with? The reason is that because the oxygen here is slightly more basic than the oxygen here. So let's draw the resonance structure of an esters. So I will draw right here. So let's draw this one out. So let's say you have an ester CS3 CO OCH3. So the oxygen here will push the electron towards the carbon. So oxygen here push the electron towards the carbon, and the resonance structure that you will get is gonna be this CS3CO minus OCH3. Okay, so oxygen has 3 bonds here, so it should have a positive charge. So you notice the electron density is slightly higher here in comparison to here. So electron density is slightly higher here, so you have a negative charge. So the negative charge becomes more basic, obviously. So as a result, we know that this oxygen is more basic because it wants to abstract a more basic, it wants to abstract a proton whenever it gets a chance. Okay, so that is the rationale behind it. So this oxygen here is slightly less basic, and that is the rationale behind it. All right, so this is what we got here. Okay, so let's look at the mechanism. What would happen? So we got our CH3 C double bond O H and OCH3. Okay, so that's what we got. So if you'll notice here, the oxygen has provided electron towards a hydrogen, towards a proton, so it has lost electrons. Shortcuts, when oxygen have 3 bonds, it should have a positive charge. So we got ourselves a positive charge here. So every time you have a positive charge, your goal should be to neutralize somehow. So how can I neutralize the positive charge? Well, I can neutralize my positive charge if I bring these two electrons back to oxygens, right? So if I do that, that's basically going backward direction. So that's basically I will make my reactant again. So if I give away my hydrogens, I will make my reactants. But let's make something different. So this is why you will find out all the step in this acid catalyzed reaction is going to be uh, in equilibriums. Okay, so let's do something different. So if there is another way I could neutralize it, so if I neutralize it by moving a pi electron from here, CO bond towards oxygen, so what would I make? So again, this is not the correct structure what I'm gonna draw right now, but I will just show you. So we draw this OH, so oxygen back, it's 2 lone pair, and you notice the carbon atom right here does not have octet anymore, so it becomes highly positive. So when something is highly positive, a nucleophile can easily attack this carbon atoms right here because it's highly positive. So you will never make the positive ion. Instead, everything happens together. So by adding the proton here, we make carbon more electrophilic. So as a result, our nucleophile, which is in this case, our nucleophile is water, is gonna be able to attack instantly. Okay, so we should put that in your note by adding the proton to oxygens, uh, we made the carbonyl carbon more electrophilic. So it wants more electrophilic. Okay, so more electrophilic. So let's draw the next intermediate. So we got our CS3, okay, so now we got OH here, and then we got our OCH3, and then we have our water. So now oxygen has 3 bonds, so it should be positive charge. Well, how can we neutralize the positive charge on oxygens? We can neutralize either by bringing back those 2 electrons back to oxygens, right? So either you lose this bond and do that. So if you do that, that's basically you are breaking the bond here. You are getting rid of your water. So that's why you will find out every step in this reaction is an equilibrium. Okay, so I want to do something different. I will bring back one of the OH bond. It doesn't have to be this one. It could be this one too. So let's do that. So you noticed here, the carbon atoms here was sp2 hybridized. So this was an sp2 hybridized. But here, the carbon atom is sp3 hybridized. So the carbon atom here is an sp3 hybridized. So this is sp3 hybridized carbon atom, sp3 carbon atoms. And what is the structure of sp3 carbon atoms? That is tetrahedral, right? So we have tetrahedral. So this is called tetrahedral intermediate. And because this is the first tetrahedral intermediate we are making, we call it tetrahedral intermediate 1. We're going to have 3 of those, right? Okay, so let's draw the next structure that we will make based on this arrow. So next one would be, so I will draw here. Again, all the steps would be in equilibriums. So we're going to have, CH3, COH, OCH3, and we have our OH. Okay, so now all the oxygen has lone pair. So this intermediate is still tetrahedral. So this is called tetrahedral intermediate 2. Tetrahedral intermediate 2. Okay, so one thing I forgot is here. So who would abstract the proton here? So a base, whoever can abstract a proton. Like remember in our reaction, the B stands for water or anything that could abstract a proton. So we just created once the B was released, we have a base here and that base would immediately abstract the proton. So B stands for anything that can abstract a proton. So here in this our reactions, we had our BH plus. Okay, so I will write down here again HB plus. So now we have lone pairs on oxygens, and we know that lone pair on oxygens loves electrons. Now anything, all of these oxygen can abstract a proton basically. But if the OH, oxygen from OH abstract the proton, that's basically going backward. So let's say this oxygen abstract, that's gonna be OH2 plus. If this oxygen abstract, that will also kind of similar, but with kind of reverse stereochemistry, but that's not the point. Let's say we attach one from here to make something different. So in the next step, we have CS3, C, OH, OCH3, and we got our OH here. So if you abstracted a proton here, so now oxygen has 3 bonds, so it should be positive. We can neutralize the positive charge by breaking the bond. Okay, so if I do that, let's say if this molecule goes away, so you noticed here our carbon atom becomes positive. It doesn't have octet anymore, no octet. So when you don't have octet anymore, what would happen is one of the oxygen, dang, I cannot pronounce octet, not pronounce, spell. So there is no octet anymore. So when you don't have octet anymore, so what oxygen will do, it will immediately provide, either one of those oxygens will provide a lone pair. Technically it's either resonance structure, so both of the oxygen can provide, but for mechanism purposes, I will just move one of the electron here to maintain the octet. Okay, so this is how the mechanism works. So you want to neutralize the positive charge on oxygen by breaking this bond. So these 2 electron moves to oxygens. To maintain the octet on this carbon atom, one of the lone pair from oxygen will move here. And you notice the carbon atom still here is tetrahedral. So this is tetrahedral intermediate 2. Sorry, not 2, 3. Tetrahedral intermediate 3. So when we do that, what will we be making? We will be making CS3, COH. Now oxygen has 3 bonds, so it should be positive. And we got our OH, and our byproduct was CS3OH, and there is still, the base is there. All right. Okay, so now why this? So why we get rid of this leaving group? So you notice here, I could have done the same thing. I could have get rid of my CS3O here by bringing a pair of electron, but why I didn't? Because if you have this as a leaving group, CS3O, what would happen? You make CS3O minus. So here it was a bad leaving group. So here CS3O minus would have been a bad leaving group. Bad leaving group, right? So here CH3O minus would have been a bad leaving group. But here CH3OH is a good leaving group, right? Because it's less basic. Good leaving group. So by protonating the oxygen here, we created a better leaving group. So by protonating, okay, I will write down here. So this portion here, by protonating the oxygens, we created a good leaving group. Okay, so that's it. So now we have a situations where we created this scenario. Okay, so what's our next goal? If you have something positive on oxygen, your goal should be to neutralize it. Well, we can neutralize it by bringing this bond here and abstracting the proton BH plus. So B stands for anything that could abstract a proton. So at the end, we got CS3CO OH plus O. I'm trying to color code properly OCH3, and I'll add the hydrogen here. Okay, so OH. So you notice this OH and H basically comes from water. So you started here. So where you have broken this bond, your OH and H gets from water. But you use acid catalyzed reactions because you want the catalyst to help this reaction, because this reaction is not going to happen just by water. It may happen, but it's not going to be as fast. It needs catalyst because ester is not very reactive. So what is the role of catalyst? The catalyst does two things here. Catalyst, by adding the proton, so catalyst makes the carbon more electrophilic. Before it wasn't. It makes more electrophilic. And also the catalyst, by adding a proton H plus, we created a better leaving group, CH3OH. We created a better leaving groups. All right, so that's it. So we will talk about more reactions in the next video.